Hey guys, today we will see the different methods of finding the roots of a function. Ever heard of the Newton's method? Yeah, we will compare 6 methods like that and we will see which one is the goated one. So what is the root of a function? It is the value that we plug into the function and we get 0 as a result. Our job is to find this value of x. We have got the 6 methods to find the value of x and we will implement that in C++ and we will compare the results. First of all, we have the Newton's method. So this is the most common method. If you are an engineer, you probably know about this. So how does this work? If you see this graph here, you will see that f of x is the function that we have to find the roots for. Now we need an initial guess, right? This n is our initial guess. If we draw a line up, the point at which this line touches this function, we draw a tangent. So this tangent extends to the x-axis and the point where it coincides with the x-axis is called the new guess. First of all, we check if the difference between this n and this n plus 1 is small enough. If it is small enough, that means we have reached the tolerance level and we exit. Next, if it is greater than the tolerance level, that means we will find the new point for the tangent line. So that means we draw a new line down here and the point where this function meets this line, we make another tangent and this continues until we find a good enough value. Now programmatically, this can be implemented by this method. And how did we find this? From the simple slope equation. We know that the equation of the slope is y2 minus y1 by x2 minus x1, right? So we just plug in these values that we find here and we set this f of x n plus 1 to 0 and then we rearrange these values and we get this equation. Now why do we use this method? Because the convergence rate of this method is quadratic. Now let's see how this method is implemented in C++. So this is the function. It takes in the original function that we have to find the root for, the derivative, the initial guess, and then the tolerance value. From this we find the value of the derivative at x. And then we check if it is 0, because if it is 0 we can't divide with it, right? So we exit out of that if this condition matches. Then we just simply plug in that equation we had in the presentation into this. We check the tolerance. If we match the tolerance, we break out of it and return the found value. Simple as that. This is the most simple equation or the function that we have in this entire video. Next we have the Halley's method. This method is very similar to the Newton's method except that we need a second derivative here. Because we are using the second derivative, it means that the convergence rate of the Halley's method is cubic. When we run this program, you will see that this method finds the solution in very few number of steps. But then there is the trade-off that we have to find the second derivative. It takes time, so it's a balancing situation. We can either find the derivative or find the solution with more number of steps. Now let's see the implementation in C++. So this function has the same signature as that of the Newton's method, except that we take in the second derivative as well. Now we find the values at x for each of these functions, f, df and ddf. It's just basic stuff. Then we find the numerator, denominator based on the presentation, and we need to check if the denominator is 0, because if it is 0 we cannot continue, right? Then we just divide it, we find the tolerance value and we return out of it. Next we have the bisection method. From this method we are introduced to the bracketing method. That means we have two endpoints, that is a and b. So these are like the two initial guesses and the actual value will come between these two. So if you see, it is much similar to the binary search algorithm that we learn in computer science. We have two guesses, we find the midpoint c, that is just a plus b by 2. Simple stuff. In this method we use this concept called intermediate value theorem. So what that does is that suppose we have 2 points a and b, it means that if either one of it is negative and the other one is positive, it means the actual root of the function will lie between these 2 points, a and b. That theorem is actually very useful for us because then we can use this expression to check if we are in the limit. So for example, in this case, a and c are actually the correct limits because beyond c it just increases, right? It is going away from the root. But inside this a and c, you will see that the root is inside these limits. So what we do in the next iteration is that we find the next midpoint, then we check again. So we find that this becomes the new a because and this becomes the b, alright? And from this we find the next midpoint. So you will see that this midpoint value is pretty close to the actual root. Then we know that we have found the actual root of the function and we exit out of the program. Let's see how this is implemented in C++. So we have this function, we're taking these two inputs a and b. Now comes the important stuff. This a value should be always less than b because we are having two endpoints, right? Either one should be smaller. In this case we are taking a as the small value. Now we use this sinum function. It just means that one of the values should be negative because according to intermediate value theorem, two values should be either positive or negative for the root to occur between these limits. First of all, we check the tolerance. We see if the difference between the previous value of c and the current value is less than the tolerance. tolerance. If it is, we break out of this. And here is the actual core of the program. You might think we are not doing any division or anything, right? It's simple stuff. First we check if the value at the midpoint is in fact the root. If it is in fact the root, that means we can return the C value. Next, we take the A value. Then we only check one of the conditions. Either f of A times f of C should be less than 0 or f of C times f of B should be less than 0. If either of these conditions pass, we do the corresponding changes. Then we return the value and that's it. This is the secant method. It's very similar to the Newton's method except that we are using secants for finding the value instead of tangents. Now the cool thing about this function is that it does not need a derivative unlike the Newton's method and the Halley's method, but the trade-off is that the convergence is super linear. That means it is close to the value of golden ratio, something like 1.68. It does share some similarities with the bisection method that it needs two inputs. That is, this n plus 1 is the A value and this n is the B value. Simple as that. Now let's see how we can implement this in C++. So this is the signature for the function. It is very similar to the bisection method. We do the exact same stuff we did with the bisection method. Now we change the formulas though. That means first we find fa minus fb. It's the same stuff we see in the presentation. We just plug all these values inside it and we assign the new values. A becomes b and b becomes c, and we check if the tolerance is reached. If we reach a tolerance, we break out of it. Next, it is the ITP method. It stands for Interpolate, Truncate and Project. Now, don't ask me to explain this. It is a wallpaper. I will show that to you. It is so long and surprisingly, it is very efficient. Now, let's see how to implement this in C++. So here we have the function. It takes in the actual function, the two values, the tolerance and these three variables. You will gain more information on this if you check the paper. I have linked that in the description and I have shown that in this video as well. Also, there is this R library implementation. You can check that also. It is actually a very beautiful library. Now in this we have all this sort of stuff. Actually it's just three processes: interpolation, truncation and projection. This interpolation is similar to secant method. Truncation is like reducing this line to some kind of limits and then projecting it to the actual root. And then we assign some stuff. In order to explain this, it's out of the scope of this video. You can check the paper as I have said earlier. You might think this function is very complex. It is, but on the other hand, it is very efficient. I think this is a very nice function. That said, let's move on to the next one. The next one on the list is the Brent's method. What I found particularly interesting about this method is that it is a hybrid one. It uses three separate algorithms or methods to find the actual root. So it uses the secant method, inverse quadratic interpolation and bisection method. So this one, inverse quadratic interpolation, don't ask me how that works, I don't know. Now let's see how we can implement this in C++. So just like the other functions, we have the same signature. It takes in the function, the a and b variables, and then tolerance and max iterations. Now one thing I want to show you is that it has three conditions. That is, this first one is the quadratic interpolation. If we match the condition, we do this method. If we do not match the condition, we do this secant method. And jumping over some lines, if we match these five conditions, we do bisection method. So yeah, this is how we use the three methods to find the actual root. This combination is called Brent's method. Alright, now that we have all these functions set up, let us test this. Today we will be using this function to check the accuracy and the speed of these functions. As you can see, the root of this function is 10 pi, which roughly gets to 31.4159 something. For the methods like the Halley's method, I have found the first and the second derivatives, and from this we will create the C++ version that will plug into all of these functions, and I am running all these tests in NanoBench with 15,000 iterations. Now this is the result. You can see that all these values are pretty close to the correct value within the tolerance range. But when we look at the time taken and the number of iterations, you can clearly see the difference. Because the bisection methods needs to find so many midpoints, it takes 31 iterations. That is a lot of iterations compared to the other methods. But then in terms of time, the Brent's method takes the most amount of time, but it only has 19 iterations. Now for the rest of the methods, we have two criteria. The Halley's and the Newton's method needs the derivative. So in that area, the Halley's method actually takes the lead because it only takes 3 iterations, but it needs a second derivative. But if you're finding one derivative, might as well find the second one, right? So I chose Halley's method. Then secant method is another section, but it takes 12 iterations. And now the ITP method. It only takes 8 iterations and it completes it in 734 nanoseconds. So I think the Halley's method and ITP method are very good algorithms. Now which one is the goated one? And it is the ITP method. Why? Because we don't need to find a derivative for that. After all of that, it finds the value in just 8 iterations and just 734 nanoseconds. I think that is a good trade-off when we consider the time taken for finding the derivative. So yeah, that's it. And once again, the ITP method is quoted. Check the paper out. And I will see you in the next one.